So we've already dealt with equations of the following, all right? Where basically it's y derivative is equal to like a of t of y plus b of t, okay? Something where we have basically one derivative right here, the original y right there, and then some extra non-homogeneous part right here, okay? So we're okay with that, we're familiar with it. And basically we've already mapped it in that way, this is the linear non-homogeneous equation, okay? Linear. Now, why again is this linear? The reason why this is linear here is because of that form right there, where basically all we're doing is we're taking y derivative, y, some extra t, and we're just adding them all together. Maybe this gets an extra coefficient, maybe you could also have had it where like this was written as ct and then you divided that out in all the other places. You know, but basically nothing really happens screwy with basically this and that. As in, we never write out something on the order of y squared times y plus e to the y equals t. So we never have an equation like that, okay? This is very nonlinear right there, okay? But, you know, most equations are not linear, all right? Most equations do not fit just this nice, simple, straightforward pattern. So we like to handle those, okay? We like to see what we can do beyond just this one very neat and tidy form which we have come to master, all right? All right, so let's do a fairly simple one, all right? Let's talk about chemical reactions as an example here. All right, let's say that I have C. I'll use that as my variable here. All right, C, this represents basically the amount of a certain chemical. Okay. All right, so let's say I have the following situation where the derivatives, all right, the rate at which that chemical is changing will equal C of t squared, okay? And this is an actual situation, okay? Like some chemicals actually grow at that level. Now what does this precisely mean? It means that, okay, the rate at which the chemical is changing is equal to the square of the amount of chemical there is, all right? Now, one thing just as a comparison is, remember what the population equation sort of looked like? It looked basically like this, where the derivative of p of t is equal to some multiple of p of t. This was like, oh, this is going to grow very quickly, exponentially fast, because, hey, the rate at which this is changing is proportional to the current size of the population. This, the rate at which this is changing, will equal the square of its current amount, okay? So one thing that we see here is this thing is going to increase much more quickly than this guy, okay? This guy is going to just go berserk compared to this guy, okay? And so one problem here is, okay, so we know at least a little bit about how this is going to behave, but how do we solve this? Because one thing here is this is definitely not linear, okay? This is squared, all right? This is quadratic, right? So how can we attempt to handle this guy, okay? How can we attempt to handle it? All right, well, let's try to handle the following. Let's maybe rewrite this part of the equation, okay? Let's rewrite this as dc dt equals c squared. All right, let's rewrite it this way. All right. So what can I do here? What can I do? Well, this is, I don't really know. It feels strange what I'm looking at here. But maybe what I can do is, there was that really weird trick I remember, where at one point we sort of separated basically the dc and dt from each other. You know, we treated those as separate things, and usually we just treat this as like one solid symbol right here, okay? But let's just try to cut this up. Let's see what happens. So let's just multiply the dt over there, okay? dc equals c squared dt. And let's divide the c squared out to the other side. So I get dc over c squared equals dt. All right, so there we are. All right, now again, this is bizarre what I'm doing here, but where am I going with this? I look at this and I think, you know, I have this dc over here, and a function of c squared, and then I have a dt. These d's, usually I just integrate those, right? You know, whenever I say a dc or dt, like, usually it's because it's in front of the integral sign. Let's integrate this. Let's integrate this. Let's see what happens. All right, so let's integrate these guys. What happens? So, all right, so on the one hand, I have 1 over c squared dc. And this is going to equal the integral of dt. All right, so what do I have here? Well, over here, I'm going to get, this is a straightforward integral right here. This is going to be -1 over c, and I'll just add a plus c0 just for the constant. And then over here, I'm going to get t. Okay, I'm going to get t. All right, well, that's something right there. And by the way, I didn't add a constant over here because I have this constant over there. That's enough. All right. Okay. Now, all right. So, well, this is pretty good because now I can just try and solve for c right here. All right. Solve for my chemical concentration. So I get -1 over c equals t minus c naught. I get c is equal to then -1 over t minus c naught, which I'll rewrite as 1 over c naught minus t. Okay. Okay. So now I have this setup right here. Now what does this look like right here? Well, I'm not quite sure really. I don't know what this c naught should be. Okay, so let's try to nail that guy down. Now if we want to nail down a constant, we need some kind of initial conditions. So I'll just add to this problem right here just some trivial initial condition on the order of c0 equals 10. All right, let's see what happens if I do that. c0 equals 10. Actually, I don't want it to be that big of a number. I'll just stick with 1. All right, so let's try, so in that situation, let's nail down the c naught. So c0, I know that equals 1, and then I'll plug in the 0 right here. So this is going to be over c naught minus 0, which is 1 over c naught. Therefore, c naught is equal to 1. All right, great. So what is my equation now? C of t is equal to 1 over 1 minus t. All right, what's going on here? What's going on here in this situation? Well, what does this look like? Well, what happens is that this guy, as t gets closer and closer to 1, will shoot to infinity, right? So here's 1. I'm starting off here at 1. And I basically just shoot up to infinity there. All right, and we also know what it sort of does on the other side there. It also sort of comes up from negative infinity and does this. All right? Now, one thing here is that we should think about this. One thing is that this negative part right here, that doesn't make sense in the context of the problem, right? Because you can never have a negative concentration of something, right? So this part doesn't make sense. And what about the singularity, though? Like, what's going on there? What's going on here is basically what happens at that 1 is that it basically suddenly shoots to infinity the amount of the concentration. Okay? Now, one thing about that is in the real world, obviously you never have an infinite amount of a certain chemical. All right? The universe is finite. You know, you can't have this infinite quantity. So presumably what happens here is that it shoots up for a long time, and then it sort of maxes out and a different model applies, all right? But basically the idea is that all of the chemical reaction that's going to be reacting is going to be done by this moment, time equals 1, okay? Does that make sense to everybody? Okay, so All right, so we got a nice little equation right there. Now I also am just sort of curious what happens if I had a different initial condition. So let's say I had, again, the same problem, ct equals c squared of t, and I have the beginning value is equal to, let's do 1/10. All right, let's see what happens there. Well, again, I can just get this here. I get c0 is equal, c at 0 is equal to 1/10. Plug that into the equation. I get t is going to be 0, and that's going to be subtracted into c naught. Therefore, 1/10 equals 1 over c naught, which implies that 10 is equal to c naught. Okay, so in this other situation, I get, as in my equation, ct equals 1 over 10 minus c, t. And again, what's going on here? Well, instead of hitting that singularity at 1 like I do here, I hit it at 10. Okay? So one thing that's interesting is that, hey, if I start off with a smaller quantity, then the singularity where basically all of my chemical reaction happens will be much later. Okay? Which makes sense, right? As in I start with a smaller amount of the chemical, and if it's growing relative to itself, that means it's going to take a lot longer for it to go berserk in terms of the amount of it, right? Okay, so that's great, that's great. We've honed in that example, and we did it using this kind of screwball technique right here, where basically we cut apart, we separated the dc and dt, okay? All right, so let's think about another kind of problem here. All right, it's going to be, again, the same kind of problem again, except I'm going to add a twist to this, all right? Let's say that instead of just it being purely determined by itself, I also make this determinant on, let's see, what I'll do is I'll erase this and then just say we have another problem. So let's say I have c, the derivative of c here, is equal to c squared, or cubed, let's make it go even faster, over t. Okay? So alright, so now we have a separate, so basically what's going to happen here is this is going to be increasing quickly here, but for some reason, actually I'll make that t squared to just up the stakes a bit. But over here, we're going to have t squared, which is going to sort of decrease this more and more with time. Okay? So what's going on here is you can imagine that, let's just say, yes, it's growing cubed relative to itself, but as time goes on, let's just say the temperature is getting lower and lower, and there's less and less ability for it to have those chemical reactions. Okay? So it's sort of like temperature is lowering, causing fewer chemical reactions, and the chemical reactions are growing relative to themselves in this way, all right, or the cube of themselves. All right, so what happens here? Well, again, let's just try to look at it using this oddball separation of variables here. All right, so we have this. Okay, well, let's try to do what we did before. We separate dc and dt. All right, so I have dc over here. And I'll divide, c cubed out of that. And then over here, I'm not just going to have dt, I'm going to have dt divided by t squared. Okay. Okay. Where are we going to go with that? Well, let's just take the integral and see where that goes. All right. All right, so let's do this. Taking the integral gives us on the one side, we just get this up. On the one side, this gets us 1 over c squared plus c naught. And then on the other hand, 1 over t squared dt, this is going to equal 1 over t, sorry, I forgot, I did this incorrectly. It should be -2. Should be -2. And then over here, this should be -t. Okay, all right, so we have that. So again, negative 2 over c squared equals negative 1 over t. All right, so let's try and solve for c here. Okay, that's going to be plus c naught. All right, so let's solve this for that. So I'm going to get negative 2 over c squared equals negative 1 over t minus c naught. C squared is equal to negative 1 over t minus c naught over negative 2. And then I get c is equal to the square root of c naught minus 1 over t. And then I have square root of 2. Okay. Okay, so I have that right there. All right, so what's going on here? Well, again, it's similar to before. All right, what does this look like here? Well, basically, when c naught, when 1 over t equals c naught. Oh wait. Wait, no, that was correct. Yes.
Shouldn't it be 1 over negative 2c squared?
1 over negative 2
C squared for that, I think, yeah.
1 over negative 2. Yes. Yes, that's right. Alright, so negative. Actually, I can just, I'll do some of the algebra here. This is in a final take. Alright, so this is going to look like 1 over 2 c squared plus c naught equals 1 over t. I'm leaving the c naught because it's just a constant, so when I took that negative, it doesn't matter. Then I get c, let's see, this is 1 over c squared equal to 2 over t. Then it's, this is going to be c squared equals t over 2, and we get c equals, excuse me, I'm forgetting the c naught. Doing a lot. Alright, that's going to stay c naught, then we have minus c naught, then I have c is equal to the square root of t over 2 minus c naught. Okay. Okay. Alright. Alright, so that's a fact. Now this is actually somewhat different than the answer we had before, because what we have now is basically now this guy here, he's basically going to look like, well, let's actually just try to calculate some c naught for some value here. So let's do c 0 equals 1. So again, so in this situation, he would just look like c0 equals 1 equals square root of 0 over 2 minus c naught, so c naught equals 1. Correct. Okay, so let's graph out here. Ct equals square root of t over 2 minus c naught. Now it's 1. Alright, so what does this guy look like? Let's see, well, where does he start? Well, he starts when t equals 2 here, okay? As in that's when it equals 0. Actually, that's... Oh, this should be plus. This should be plus. Okay, so he starts off at a negative value over here. He starts off at when t over 2 plus 1 equals 0, that's t equals negative 2. So he starts off at negative 2, and then he increases like this. Okay, with this square root speed. Alright? So in this situation, what's interesting is that, oh, well, yeah, this is in a sense growing very quickly relative to itself. It's like super exponential because of that cube right there. But because it's being divided by time here, because in a sense, as time moves along, it's sort of having less and less ability to have further chemical reactions, it's actually growing pretty slowly. Growing, and getting, in a sense, indefinitely large, but just not very quickly, as in this isn't even linearly quickly, this is the square root of something right here, okay? Okay, so we've seen so far now some of the power of the separation of variables that we did. Where basically, like we saw, okay, I have this c cubed, I have this t squared, let's just split that up. Let's see where this goes, okay? All right, so let's see what happens when we have a more general problem, okay? So I guess the most general sort of problem I can come up with here is use y derivative. You can imagine this is still chemicals, okay? And you have basically two functions here. You have some function in terms of y, and some function in terms of t, all right? Okay. So what do we do with this right here? Well, again, you can basically just think of this as dy dt. We cut this up, all right? So we end up with dy over ay equals dt over b of t. We integrate both sides, and then we get basically two functions on either side, okay? Just for the sake of it, I'm just going to have something like big A of y here, and this is going to be big B of t. And that's what basically the integral here equals, okay? And what we then would like to do in basically most of these situations is, like over here, after we got everything out, we then want to find out, okay, well, let's try to isolate C, right? So we do some subtraction, we do some multiplication, we do conversion, we take the negation. We undo all of this stuff in order to basically get C by itself, right? That's what we did before. So in here, in this more generalized situation, what we'd like to do is to isolate y and then have A inverse of b of t. All right, we like to take the inverse of this function a. All right, but one thing is a is not always very nice. Okay, and one sort of inkling that you could get that you won't always be able to do that or do that in a way that's useful is actually right here. All right, when I had the c squared, I took a square root, right? I took a square root. But that square root had a positive and negative part to it, okay? I threw away the negative part because, this is a chemical situation, so there was no use for the negative part, but there's lots of applications where the negative part does matter, where it has real meaning, like position. A negative position is a real thing. A negative amount of money is a real thing, okay? So you can't always invert it. You'd have to just leave it in this form if you want to have all of it, all right? And let me do an example of that. You could have a situation where you want to do, okay, dy dt is equal to y squared plus, actually let's not do it that way. Let's do it as, I'll do it this way. I'll have y squared plus ey, and then t plus sine of t. Okay? All right. All right, so what happens with this guy, right? What happens when I have this guy? Well, all right, let's do our separation of variables here. I'm going to move this over there, this over there. I get integral of y squared plus ey dy is equal to the integral of t plus sine of t dt. Okay? All right, so this guy right here I can do very straightforwardly. That just turns into y cubed over 3 plus ey plus c naught. And then over here I get t squared over 2 minus cosine of t. Alright. Alright, so I have now these two sides and they both equal each other. There is no chance in hell that I'm basically going to get y by itself, okay? There's no way. Because I mean, look at this. You have a y cubed and then plus an ey. Alright? There is no way that you can now just get y. Alright? Maybe you could come up with some weird function that sort of did it, but not really. Not really. And especially if maybe it looks something more like this, you know, even bigger of a mess, okay? So sometimes we're just going to have to leave it in this form because there will not be an inverse to A. Alright, there will not be an inverse to big A. And this is one of those times where we just have to leave it as it is in its full ugliness, okay? Now, one thing about this is you can calculate it, okay? As in, if I had a certain t, it'd be fairly straightforward for me to find out what the y would be for that. But as it stands, there's nothing I can really do. Okay? Does that make sense? Okay. Alright, so that's an issue with separation of variables, alright? Is that sometimes you don't always get a nice straightforward function. Now even in this situation that I made here, you can maybe solve for like c naught. So like one thing is like, let's just say that y of pi is equal to 1. You know, let's say we had that situation. I could figure out what c naught was. Now how would I do that? Well, I know that y, now another way of writing this, by the way, is y of pi equals t. Okay? So I know that when pi equals t, y equals 1 right here. So that means, okay, I'll place 1 here, place 1 here, replace pi right here, replace pi right here. Alright? And then it'd be very straightforward to find out exactly what c naught was. Okay? Alright? That's what c naught is. Okay? Alright, so even in this sort of situation, at least you can still find out, you can still nail down variables like that. Okay, so that's separation of variables. Alright. So, where do we want to go from here? Well, one thing is that even like that form that I just finished writing up is very nice. You know, like as in basically the condition for being able to solve the separation of variables is you had something like dy dt, and you have then something on the order of ay bt. You could also write it the other way around if you want, okay? Now, one thing about this here that makes it very nice is that ay, basically everything that's y is on top, everything that is t is on the bottom. They're all nicely separated. They're both nicely segregated from each other, okay? And what that got us was a situation where it's like, okay, we can separate these guys. We get dy over ay equals dt over bt, and then we can do the rest of our work, okay? That was nice. That's a nice feature of it. But, again, just like I said about the linear equation, is that, it's nice that we can handle that problem, but not all problems look like that, okay? Not all problems look like that. And another sort of problem that we could be confronted with is one where these two guys are not nicely separated from each other, where these two guys are intermingled in more profound ways, okay? And let me just throw up a good example of that. that could just be something along the lines of you have dy dt is equal to, let's write this as negative 3y minus et over 3t plus cosine y. Okay? Now, one thing is that, here, it might have not been obvious that, two things were separated. Like, it could have been something weird where it looked like ty over, I don't know, y squared plus 1. Like that's not obviously in this form. Very quickly you can get it in that form by doing something like t over y squared plus 1 over y, and then it's in that form, more or less, where, okay, all of the t is on top or on bottom, all of the y is on top or on bottom. So here it wasn't obvious. Here it was like, okay, I can put this in this form. There's no way I can put this in this form, okay? It's just not happening, all right? And by the way I like to at least interpret this sort of problem is that, y is my position. This is one sort of interpretation that could happen. T is time, dy dt is equal to, let's call it velocity. And then this thing over here, this is call him fty. This guy over here, I just like to think of him as, basically some my current velocity at y at time t. Okay? So in a sense you can imagine that this is something along the lines of, here I'm particle, and basically sort of just moving around along the line, at different points, dependent on what the time is and what the position is, right? Okay, does that make sense? So this is a very sort of real world problem. This sort of thing comes up, okay? And you can imagine that that can be a real mess because it's dependent on not just what my current position is, not just what the current time is, but both position and time, okay? It's changing within both time and position, which makes it very complicated, okay? Okay, so I look at this problem now, and I feel, okay, there's no separating these variables, okay? There's not a chance. So what can I do? Where can I go? What can I do in order to move this around? Well, one thing is maybe I can rewrite this a bit. Maybe I can play around with this and get into a better form. Because, like I remember, at least when I was doing the non-homogeneous equations, like I moved things around, I got things in a different form, and I was like, okay, then I could, maybe if I added something to it, I could get the inverse product, no, excuse me. Then I could use the inverse product rule, okay? So maybe I can mix this around and I'll get some insight from that, okay? So, you know what the hell, I'm gonna multiply this over there and then add this over to that, okay? So let's see what that would look like. I have 3t dy dt, that's multiplied by this guy, okay? So I get 3t plus cosine of y. And I'm also going to add on this part. Plus 3y plus e of t is equal to 0. Okay? So I have this dy t right here, this guy, and this guy. Okay. So, alright, so what can I do with this? What's an idea here? Bless you. Well, one thing is that when I look at this, I see that, okay, I can't really do like that product rule thing that I had from before, right? Because the product rule, one of the things about it was that, oh, I have the dy dt derivative over here, and then I have the y over here. And then somehow I was able to get, a t and the t integral over there, okay? But here, there's a y here, but there's also the e of t. There's over here, there's the t, but there's also some y stuff mixed in. So I don't think that's going to fly. I don't think that's going to fly. So what can I do? Well, I think, okay, product rule, that's not going to work. But what other stuff is there? And I think, well, this, what is this sort of thing, what's another sort of idea here? Or what am I looking for in terms of a solution, right? What am I looking for in terms of solution? That's helpful to know, like, what I want. Usually, I'd say that I want my solution to look something like, y of t is equal to some function of t. That's usually what I have. But, as we saw with the separable equations, it could have been a real mess, like, a of t is equal to b of y. It could have been a mess like that. And hell, it could even be a bigger mess that looks more like something like this. Phi ty equals 0, okay? Now, what do I mean by this? This big phi, and you probably pronounce that as F-E, that's how you pronounce it. What do I mean by this? I mean, it's something like monstrous, like cosine t plus y squared plus e to the t equals 0, something like that. Some whole big monster like this. That I can't even separate all the t's and y's from each other. They're all sort of locked together in this horrifying way. All right, so this is in a sense what I'm looking for, is some sort of solution like this. Now, one positive thing about this form is, yeah, it's a mess, but if you told me what t is, I could probably tell you what y is, or at least give you one or two candidates, right? If I told you like t was equal to pi, you could give me a good guess as for what y was, okay? So it has advantages, this form. All right. Now, okay, so I'm looking for something like this. All right, I'm looking for something like this. Okay. All right. So how is this related to this sort of equation? Well, if I took the derivative on this guy, what would that look like? It would look like phi d dt. All right, or actually, I'll write that this way. Phi of ty. All right, and we'll take the derivative on this guy. I know he's equal to 0 on one side, so hey, the derivative of 0 is equal to 0. So I know one side of it. And then what happens here is, okay, I'm going to get the t partial derivative of phi, okay, as in the derivative with respect to just t. Now I'm assuming a very slight amount of Calc 3 in terms of just how this works. I'm just going to, now, have you taken Calc 3?
I'm taking it right
Oh,
now.
oh yeah, I forgot. Yeah, you're in my class. Okay. 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 Okay, so I'll come up with a good explanation for this later. But basically what happens is that when you want to take a derivative on something with two variables like this, you have to take the derivative on both parts of that, okay? So for instance, if I had a function like fxy, and both of these guys, actually, I'm just going to assert this right now, okay? That, which, that's my cardinal sin, is I'm not allowed to just assert things, but this time forgive me. Is that I'm going to have ty right here, okay? The derivative with just respect to phi. And I'll explain exactly what I mean by that in a minute. And then on the other side there, I'm going to have the derivative with respect to y, okay? The y part of this, and then I'm going to take the derivative with respect to the y inside of it, okay? Now why am I doing this exactly? The reason why is because, hey, I have this function phi. I want to see how it's changing with respect to t, all right? Now I take the derivative and I think about, okay, well we have to take the derivative for the t part, obviously. obviously. So yeah, this makes sense, all right? Normally I think that it would just be like that. But the thing is, this y right here, this y, you remember, is dependent on t, okay? So in order to complete this, I have to also take the derivative with respect to y, okay? And then multiply that by the y with respect to t, okay? This right here is the chain rule, right? We took the derivative with respect to y, and then we took the derivative of y with respect to t. All right, another way I could write this out is sort of like as d phi dy, dy, dt, and we feel like, oh, well, those partials cancel out. Okay? Is that making some sense there? So, and just to again be sort of a little clearer about exactly what I mean when I'm doing all of that, the idea is, let's say phi looked like something along the lines of t squared plus y equals sine t plus y. Let's say it would look like something like that. Okay? What would the dt derivative look like here? Well, I'd have to take the t derivative with respect to everything. So I get basically 2t, then y doesn't change with respect to t technically, so that'd be 0, right? Y does not change with respect to t, you know, just in this situation. Then I say, okay, then I take this derivative right here, and I say, okay, this is going to equal, this y is constant, so I'm just treating this as sine t plus some, sine of t plus some constant, so that turns into cosine t plus y. All right, that's going to be 1/2 of it. And now I'm going to take the y derivative on all of this, and basically, okay, this has no y part, so that gets killed off. This has no, this is a y, so that's just going to be 1 right there. This right here has a turns into cosine of t plus y. And now I'm going to multiply all that by dy dt. Okay, like that second part right there. Okay? Alright, and then that all turns into basically 2t plus cosine t plus y plus dy dt times 1 plus cosine t plus y dy dt. Okay. Okay. So does that make some sense, that sort of procedure right there? How all that fits together? Kind of. Alright, so that was a bit of a mess, that last part. Okay. But let's try to move on. Now one thing is that, okay, so we have some understanding of what's going on there, hopefully. And we look at this part right here, okay? As in this is pull back. We're trying to solve this equation right here, where this thing multiplied by dy dt plus another thing. Alright, this should be what our solution looks like, phi ty, alright? Some sort of big mass of t's and y's that then all equals 0. Okay. So, alright, so if this is my solution, or what it looks like, when I took the derivative on t, what do I get? Well, I get this derivative of t phi right here, plus the derivative of phi with respect to y times dy dt. When I look at it over here, I see, hey, I have the dy dt times a function plus another function, right? So it'd be really great here, it would be really killer to get out of this is that, hey, what if this part right here equaled the y derivative of phi, and this part right here equaled the t derivative of phi, right? Because then I could then figure out, okay, what's the underlying phi given these two derivatives? All right? What's the underlying phi given those two derivatives? Alright, so let's just think about this for a second. Now, one thing is I want to see that, because there's no guarantee in a sense that this is the derivative of some phi, of the y derivative of some phi, this is the derivative of y derivative of some t. And since the idea here is that here's my phi, alright? On one side I took a t derivative, in other sense I took a y derivative, okay? And these gave me these guys. T phi, phi t, and t phi. So this is y. Okay? Now, one thing is I would like to basically go from these, I'm hoping, that this right here is equal to this guy, 3t plus cosine y. And this right here is equal to, oh, I reversed it, I apologize. This is 3y plus e of t. This right here is 3 of t plus cosine y. That's what I'm hoping. I'm hoping that these guys equal it. How do I check that? How do I check that? Well, one thing that I know is that, hey, the t derivative and the y derivative of something, that will also equal the other order of that, okay? So basically the idea is, hey, it doesn't matter which order you take these derivatives, they'll give you the same thing. So if it turns out that, oh, I'm dealing with something here, which is the y derivative of something, and something here, which is the t derivative, then the y derivative of that and the t derivative of that will equal. Okay? So what we want here is basically now is to check, like, okay, if I take the y derivative on this guy here, and I take the t derivative on this guy here, will they equal? Will they equal? Because if it turns out that these guys equal, then that means that these guys do equal some phi, and then I can go hunting for it, okay? Then I have a right to go hunting for that phi, all right? And we'll talk about how we hunt the phi, but let's first get our hunting license, okay? All right? So, all right, so let's see. Is it? Is it? Well, let's take the y derivative on this guy. The y derivative on this guy will give me 3, right? Y derivative on 3y. Y derivative on et, 0. What does the t derivative on this guy give me? Okay? What does the t derivative on this guy give me? Well, it gives me 3. And then the t derivative on this is 0. And congratulations, 3 equals 3. Okay? So hey, I have my hunting license. I know that I don't have to hold a question mark over these guys anymore. Okay? I know that there's some underlying phi, or overlaying phi, that results in this guy and this guy. Okay? Alright? So, how can I find him? How can I get him? How can I get that glorious phi, which will then be the solution to my problem? Well, in the following way. This is how I'll do it, okay? If I think about how did I go back from derivatives originally? Okay, how did I go back when I took derivatives back in the day? Or let's put it this way. I have this phi of t. Alright? What would I do in order to get phi again? Well, one thing that I feel is obvious is, well, I have the derivative. I want to get phi, so let's take the antiderivative. Let's take the integral. Alright, let's take the integral of this guy with respect to dt. Alright, now what is my phi t here? That's going to be 3y plus e of t. Oh, excuse me, I got that reversed. This is cosine of y dy. Okay, so where do I go with this guy here? Okay. So that should be 3t right there. Okay, so I have this guy. Let's take his integral. All right, so integral of 3t with respect to dy. That's just going to be 3ty, right? Because 3t is constant with respect to y. There is no y variable here. So this is basically just a constant with respect to y here. Okay? So 3ty is one part of it. Then I have cosine of y. I take the integral and the cosine of y. That's just going to be sine y here. All right? And now I have one more thing that I'm getting out of this. Okay? I have one more thing that I'm going to get out of this. I have a constant here, okay? But this constant is more than just this constant, okay? Because when I took this t derivative here, it killed off more than just the regular old constants, right? Because let's just say I had like t squared plus e of y, all right? And I'd done t on that, okay? On this guy, it would have turned into 2t. On this guy, it would have turned into 0, right? Since this has no t's, this is a constant with respect to y, and it gets slaughtered. Okay, it gets slaughtered. So basically, any function of y that would have been there, any function of y is going to get wrecked. All right? So, when I took this integral right here, I'm not just taking the constants, I'm taking the constants with respect to t. And what are the constants with respect to t? Functions of y. Functions of y. Alright? So, now I see, okay, so this right here, this integral of phi right here, this is equal to phi is equal to the integral of the derivative of phi. And I get this. And now I have this ambiguous portion right here, which I don't know about, okay? All right, so how do I figure out what this guy is, okay? Well, let's see, what have I just done? What have I just done? I was at t right here, or was I at, oh, I'm sorry guys, I sort of reversed this. That was 3t, how did I, let's see, this should have been y dy, and then this is t. Okay, sorry about that, I reversed the y's and t's. Okay? Okay, so, alright, so what did I do here? I took the integral with respect to y of the y derivative. So I started off here, and I took the y antiderivative, right? Alright, so I'm up here. What can I do with that? What have I not used? I haven't used this guy yet. I haven't used this guy yet to figure him out. So let's use him. So how do I go from here to here? Oh, take the t derivative. So let's do that. Okay, let's do that. Let's take the t derivative on this guy. On this guy. Alright, so what does that look like here? That's going to be, so the t derivative, alright, in the following way. T phi, on one side, this is going to equal 3y plus et. I know that's one side of it, alright? On the other side of it, it's going to be this derivative right here. So, that's going to mean I'm going to get 3y, right? Because t derivative of this will just equal 3y. T derivative of this equals 0. T derivative of this equals g derivative of t. So I see, okay, this equals that. These two cancel out. G derivative of t is equal to e of t. Kill-er. Alright? So now I know, hey, g of t, that's just equal to straight up et. Alright? So now I know that phi, which is this right here, just equals 3ty plus sine y plus e of t. Okay? And well, there's one other thing. I still haven't gone back to that original constant. Still haven't gone back to that original constant. That constant's still floating. Okay? But now I have this. Okay? And that is the solution to this particular problem. Okay? Now, all right. So what's the general principle here? All right. What's the general sort of idea behind all of this? Let's do this a little more abstractly instead of using these sorts of numbers. Let's think about it a different way. The basic problem that we had. Also erase this over. The basic problem that we had was I had dy dt. I had some m ty, some sort of function of both t and y. I had some n ty, and all that equaled 0. Okay? And maybe the original way I was presented with this was something like dy dt equals negative nty over mty, and I had to split up this myself in a sense. Okay, that could have been the situation. But in a sense, this is another way of writing the same thing. Okay, this is the more natural way that nature will give you is, hey, the rate of change of your yt will be some mess of t's and y's, and then you yourself have to cut it up nicely like this, okay? But you see that if you do cut it up nicely, you get something like this, all right? Okay, so okay, we have this problem here. This problem. Where do we go with this problem? Well, we realized the idea is, hey, I want my solution to look something like this. All right, some function of t's and y's equals 0. All right, because my solution could just be that big of a mess. All right, so where do I go with that? Well, I figure, well, okay, well, if that's the way it is, if this is what the solution looks like, what does that mean for it? Well, if I take the derivative of phi here, and I remember that y is dependent on t, then I know this equals 0. On this side, it equals the partial with respect to phi, that's just the derivative with respect to t, okay? ty plus the partial with respect to y of phi ty, and then dy dt, okay? And this right here is the same form as that right there, where let's hope this equals n and this equals m. All right, that's the hope. All right, so what we have here, this is how we start off the situation. We have n and m. All right, we are hoping that secretly there is a phi up here where this will equal, where the derivative with the partial of phi with respect to t will equal n, hopefully, and the partial of what the partial of phi with respect to y will also equal that. Okay, I'm putting these dotted marks to say that we don't know that. We haven't guaranteed that. Okay. And the way we figure that out is that, well, we know that this is the case, that it doesn't matter the order of these guys. So if it turns out that really this guy equals that and this guy equals that, then that means that, hey, this guy, this y, that's m, equals this guy, which equals n, like this. Okay? That's what we're hoping for. That's what we're praying for. All right? Now, if that's true, if it turns out that I go for my y derivative here and my t derivative there, that these two guys equal, they lead to the same thing, then that means that this is no longer a dashed line. This is the case. Now it will happen, it does happen, where this is not the case. Okay? It does happen where that is not the case, and then this is not justified. Okay? There are tricks to get around that, but if basically this does not go, that does not go. You do not have your hunting license. Alright? But let's say it does. Let's say it does, if these two things are equal right here. Alright? Then, where do we go? Then, if we know that, and we can erase those question marks, then we say, alright, I have at least this is one way I think of this sort of problem, is that I have in a sense sort of two snapshots of phi. Okay? And what happens is that I can take the derivative on t and integrate it with respect to t, which is equal to m. I'm doing that as m. No, n. dt. And this will equal phi. And alternatively, I'll reverse the order of that. I like it better over here. Phi, which equals phi, which equals the y of phi dy, which is m dy. Okay? Alright? And what's going to happen here is that this part right here will be an incomplete picture. Okay? This part right here will be like some sort of like fxy plus then some pure function of gy, which I have lost, right? Because I took a t derivative here. Integrating it will not get me that back, okay? That is information which has been lost in the t derivation. And alternatively over here, I'm integrating the y derivative, but that integration does not give me, this should be yt, that integration doesn't give me back the t information, okay? And it says this is ambiguous here. I know this is solid fact. Actually, I should write this as like f1, f2, because these two guys will differ to a degree, okay? And what it is that I hope that, okay, they both have something in common. But this guy will tell me more about this part of the picture, maybe. And since this, in a sense, represents the ambiguous part of the y picture here, this part tells me this is the ambiguous part of the t picture. And what I'm hoping is that they'll have something in common between them. And there'll be a pure y part that I'll learn from here, and a pure t part which I'll learn from here. Okay? And through that process, I'll eventually figure out what phi is. Okay? And then I'll be done. Okay. Let's see. I think that's good for tonight. You guys feel good with that?